Welcome back. Today we're going to be looking at topic 5.4, and we're going to be looking at independent and dependent events. Now, before we get into the examples and the definitions, I want to draw your attention back to your formula sheet. So on your formula sheet, you have 4 formulas that we use for probability, and we looked at 2 of them yesterday. So the first 2 we looked at here, the first formula had to do with mutually exclusive events, and the second one was not mutually exclusive events. And if you notice, we were looking at or situations yesterday. So mutually exclusive and not mutually exclusive. Today, we're going to be looking at independent and dependent events. So the first formula represents independent events, and the second one represents dependent events. And if you look at the set notation there, these are going to be and situations. Now, while we're looking at or and, when it comes to using these formulas, a lot of times we will use one formula to help us find information for another. So if you notice here in this formula here, we have the probability of A plus the probability of B minus the probability of A and B. Well, this A and B might help us for other formulas. So while we have 4 separate formulas, there are times where we're going to be using 2 together or using multi-step problems. All right, so before we get into some examples, let's take a look at the definitions of independent and dependent events. So first of all, we're going to start off with independent events. And 2 events are considered to be independent if the knowledge that one event has occurred has no effect on the probability of the other event occurring. So for example, if we're flipping a coin and picking a card from a deck of cards, the flipping of the coin and the pulling of a card from a deck of cards will have no impact on each other. I could also talk about rolling a die and flipping a coin. The outcome of rolling the die will have no impact on the outcome of flipping the coin. Now, another one that's quite common is when we're talking about 2 cards with replacement. So if I have 2 cards and I draw a card out, look at it, put it back, and then draw again, I haven't changed the amount of cards in the deck, so I haven't impacted my outcome for the second round. The formula for probability of A and B is the probability of A times the probability of B. And so there would be our formula right here. That's also the same formula that is on our formula sheet. So we've got the probability of A and B. This is for independent events. All right, so let's take a look at dependent events. All right. Now, before we get into dependent events, it's also important to notice that when we're looking at independent events, tree diagrams come in really handy, and they actually also come in handy for dependent events. In the next lesson, we're actually going to spend an entire lesson just looking at tree diagrams and tables and other methods of solving probability problems. All right, so for dependent events, events are said to be dependent if the knowledge that one event has occurred changes the probability of the other event. And the most common one that we look at is having 2 cards pulled from a standard deck of cards and we don't replace. So in other words, I pull the card out of the deck, I take a look at it, and I keep it out of the deck before I pull my next one. In doing so, I'm actually changing the number of cards that are in the deck, so the outcome of one event has a direct impact on the outcome of the other event. All right, so we're going to talk about conditional probability. If 2 events are dependent on each other, okay, so this is what we're talking about without replacement, then the probability is considered conditional. In other words, the probability of one event occurring has a direct impact on the other. So the way that we would read our formula, the probability of A and B is the probability of A times the probability of B given A. So that's the probability of B given that A has occurred. So we can look at an example here. One card is drawn from a deck of cards and is not replaced. So automatically that makes this a dependent situation. And if it's dependent, that means we're dealing with conditional probability. A second card is then drawn, and our events, A and B, event A would be the first card is a diamond, and event B would be the second card is a diamond. Well, the probability of A is 13 out of 42 because there's 13 diamonds in a deck, and that reduces to 1 over 4. But probability of B changes because we didn't put the card back in the deck. So the probability of B depends on whether the event A occurred or did not occur. So we write this as the probability of B given A. And so that's our conditional probability. And so it says we denote the probability of B given A, the conditional probability of the event B, given that the event A has occurred. And so in this case, the probability of B given A is 12 out of 51. So there are now 12 diamonds in the deck out of 51 cards. So there's 12 diamonds out of 51 cards because there's now one less diamond in the deck and one less card in the deck. We can also say that the probability of B given A not occurring would be 13 out of 51. So the probability of B given not A, and so you'll see that as A prime or you'll see it as A bar. They mean the same thing. That means that there are still 13 diamonds in the deck out of 51 cards. Now we don't use this probability as often in this lesson, but you will see it when we get into looking at tree diagrams. All right, so let's take a look at some examples here. Example number 1, we're just going to be classifying these as independent or dependent. So first of all, it says classify the following events as dependent or independent. So I'll fix my spelling mistake there. It should say as. So the first one says the experiment is rolling a die and tossing a coin. The first event is rolling a 3 on the die, and the second event is tossing a heads on the coin. Now, the outcome doesn't really matter. It's the experiment itself we're looking at. We're rolling a die, and we're tossing a coin. One outcome does not impact the other, so this is an example of independent. Now, the next one, it says the experiment is choosing 2 cards without replacement from a standard deck. The first event is that the first card is a jack, and the second event is the second card is a jack. Again, the outcomes or the events don't matter. It's the experiment itself. And so without replacement means that one outcome depends on the other. So this is a dependent event. Let's look at the third example. It says the experiment is choosing 2 cards with replacement. That means we're keeping the size of the deck the same from event to event. First event is that the first card is a jack, and the second is that the second card is a jack. Again, I don't care about the events. I care about the experiment. And so independent because one outcome does not impact the other. All right, let's take a little bit deeper look at conditional probability. So the question here says a blue die and a yellow die are tossed and the outcomes are shown in an array. So I've got the sample space written out. This would be what we would call our sample space. And then we want to consider the following events. So event A is that the sum of 2 dice is 10, and event B is the number on each die is the same. So I'm going to circle those events. So event A I'm going to circle as green, and event B I'm going to circle as blue. So event A is the sum of 2 dice is 10. Well, we have a 10 here, 6 and 4. We have a 10 here, 5 and 5. And we have a 10 here, 4 and 6. Now, if we look at event B, the number on each die is the same. Well, that's our doubles. So 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. And so you can see already that there's an overlap there. We'll deal with that in a moment. All right, so it says to list the outcomes for the following events as subsets of the sample space. Well, for event A, we can have a 4 and a 6. We can have a 5 and a 5. And we can have a 6 and a 4. So we list our pairs, and then we put the little squiggly brackets around. Now for B, the number on each die is the same. Well, these are our doubles. So 1, 1, 2, 2, all the way up to 6, 6. And again, because this is a set, we use our squiggly brackets. Now, the outcome for, or the sets for A and B, this is just our overlap there, 5, 5. And again, it's still a set, so we're using our squiggly brackets there. Now let's go through and list our probabilities. Well, the probability of event A is 3 out of 36. So there are three times where the sum of the two dice is 10. So 3 out of 36, but we always put that in lowest terms, would be 1 over 12. The probability of B occurring is 6 out of 36, which in lowest terms is 1 over 6. Now the probability of B given A. So the probability that we have the same number on the die given that the sum of the two dice is 10. Well, the sum of the two dice is 10 is 3. So there are 3 times where the sum is 10, and out of those 3, one of them is doubles. So this is going to be 1 over 3. These are the ones that are usually tricky. So I'd put a star by 3 and I'd put a star by 4. Now, for the second one here, the probability of A given B. So the probability of A given B, well, that means that we already know that we have the same number on each die. So there are 6 times that there is the same number on each die, and of those 6 times, one of them sums up to 10. So this is going to be 1 over 6. Now what you might want to note is that the B value here was 6. That became our denominator. The A value here was 3. And so you'll see this a few times as we go through some of the examples. Now the probability of A and B happening is 1 out of 36. And the probability of B and A happening is also 1 out of 36. So order doesn't matter when we're talking about and, but it will make a difference when we're talking about conditional probabilities. So let's just verify this using our independent formulas. In this case, our dependent formulas. So the probability of A and B, when we write that notation, I'm just going to go back up here. When we write that notation, probability of A and B, the probability of A is first, so we write the probability of A, and then it's the probability of B given A. But if we're talking about the probability of B and A, notice the B comes first, and then it's A given B. And so if you notice in here, the probability of B given A and the probability of A given B are different values, but we're still going to come out to the same answer when we're looking at the probability of A and B, or the probability of B and A. And so you'll see how that plays out here right away. All right, so for the first question here, we've got the probability of A and B, which we already know is 1 over 36. The probability of A is 1 over 12. And the probability of B given A was 1/3. Well, 1/12 times 1/3 is 1 over 36. The probability of B and A is also 1 over 36. The probability of B was 1 over 6. But the probability of A given B was 1/6. So different probabilities multiplied together, but leading to the same result. And so down here it says, note that the probability of A and B is equal to the probability of B and A, even though the calculations are different. Okay. All right, let's continue on with some examples here. So we're going to look at some card questions here where we're dealing with replacement and without replacement. So the first question says that 2 cards are drawn without replacement from a standard deck of 52 cards. Determine the probability of the following events. The most common mistake when we're dealing with questions with cards is not reading carefully and seeing whether it's with replacement or without replacement. That's an important piece that determines which formulas we use. And so often in a question, it's not going to be bolded. So it's really important that you read and then you highlight or underline or pay attention to those key points. This one says without replacement. That means this is a dependent event because the outcome of one event affects the other. So the first question says to determine the probability of getting 2 black cards. So both cards are black. So the probability of black and black. Well, the probability of getting a black card the first time is 26 out of 51, or sorry, 26 out of 52. Now you can write that as 1/2 as well, because half your deck is black. I'm going to just keep the standard here for now, just to help with the explanation purposes. Now we have 26 black cards out of 52 black cards, but we're not going to put that card back in the deck. So that means we now have 25 black cards out of 51 cards in the deck. And so this gives us 25 over 102. So you would put these in your calculator and then use MathFrac to get your final answer. Well, what about the probability that neither card is a heart? So that means no hearts and no hearts. Well, there are 13 hearts in the deck, so that means there's 39 cards that are not hearts out of 52 in the deck. Whatever non-heart we pull, we're not going to put it back. So that leaves us with 38 out of 51, which is 19 out of 34. Now, at any time as we're going through these examples, I'm going to be giving you quite a few examples. Feel free to pause the video and try some of these on your own, and then come back and check your answers. All right, the next question says the first card is a queen and the second card is a 7. So the probability of a queen and a 7. And notice it's very specific, first card, second card. So probability of queen, there are 4 queens in the deck out of 52. And there are 4 7s. However, we've already taken a card out and not put it back. So we have 51 cards in the deck. So that leaves us with 4 out of 663. Now this last question here is slightly different than the one right before it. It says one of the cards is a jack and the other is a 4. Notice in part C it says the first card is a queen and the second card is a 7. We're very specific on order. This time it just says one is a jack and the other is a 4. So that means we can get a jack and a 4, or we can get a 4 and a jack. So we have to consider both scenarios. All right, so that means we're looking at the probability of a jack and a 4 plus the probability of a 4 and a jack. So probability of a jack is 4 out of 52. And then the probability of a 4 is 4 out of 51 because we didn't replace our card. Now the second option would be getting the 4 first. So 4 out of 52 times 4 out of 51 gives us 8 out of 663. You notice that's just double what the probability was in C. Now, what if these same questions were asked, but we had the cards being replaced, so with replacement? If the 2 cards are being drawn and they are being replaced, this is now independent, so we don't have to consider the conditional probability. So first one, both cards are black. So probability of black and black. There are 26 black cards in the deck out of 52. And we're putting that card back, so that means we still have 26 cards out of 52. Or you could think about that as 1/2 times 1/2, which is 1/4. Again, you can write this in lowest terms right off the bat. Sometimes people will find it helpful to deal with the numbers in non-simplified form because it's easier to see the subtractions that are involved in the connection between the numbers. All right, part B says the first card is a queen and the second card is a 7. Again, we're specific on order, so queen and then 7. Well, there are 4 queens in a deck out of 52 cards. So 4 queens in a deck out of 52 cards, and then 4 7s in the deck out of 52 because, again, we've replaced the card each time. So that gives me 1 out of 169. Now, what if one of the cards is jacks and the other is 4? Similar to our question before, we have a jack and a 4, or we have a 4 and a jack. So we have to consider both scenarios. So probability of jack and 4 plus the probability of 4 and a jack. So that's going to be 4 over 52 times 4 over 52 plus 4 over 52 times 4 over 52. Now you can put this in your calculator all in one step. You can also simplify a little bit as well. Figure out what 4 over 52 is, or 4 over 52 squared is, and then multiply by 2. So if you're understanding the math behind this, you can shorthand it when you put it in your calculator. Either way, you're still going to get 2 over 169. So again, when you're looking at the difference between independent and dependent, the biggest difference is that denominator in the second event. We have to change those numbers depending on what our event was. So it is really important that you don't mix up mutually exclusive and independent events. These are not the same thing. And so mutually exclusive means we're looking at whether or not two events can occur at the same time. In other words, we're looking for an overlap. So mutually exclusive events, we would be dealing with a Venn diagram and there would be no overlap. And when we're talking about mutually exclusive, we're talking about or. With independent events, we're looking at whether the outcome of one event has an effect on the other. Okay, so we're looking at the two events and we're just asking, does one outcome impact the other? Mutually exclusive, we're looking at the actual events and asking ourselves, is there an overlap or not? All right, so just because they are different terms doesn't mean we don't use them together sometimes. And so here's an example where we're given the probability of A, the probability of B, and then the probability of A or B. And we're going to determine whether these events are mutually exclusive, independent, both, or neither. These are really common questions to be asked where you're given the probabilities and essentially you're just being asked to use the formula to determine whether they fit one of these criteria. So first of all, if they're mutually exclusive, we have to go back to those formulas, and the mutually exclusive formula was the probability of A or B equals the probability of A plus the probability of B. And this is why it's important on your formula sheet you understand which formula represents which situation, so you know which ones to use when you're asked. All right, so we're going to use the left side, right side method here. And so we're going to look at our left side and our right side of the equation. And so for the probability of A or B, the probability of A or B is 3/5. The probability of A is 1/3. The probability of B is 2/5. Well, if we add 1/3 and 2/5 together, we get 11/15. So those do not match. So these are not mutually exclusive events. That means that there is some type of overlap. All right, so if they're independent, then we're looking at the probability of A and B equaling the probability of A times the probability of B. Well, we haven't been given the probability of A and B yet. We know it has to have a value because there is some type of overlap. So we're actually going to use our non-mutually exclusive formula first to figure out what A and B is. And so this is a situation where you're going to have to use two formulas to get to your final answer. So the probability of A plus the probability of B minus your overlap. So we plug in what we know. The probability of A or B is 3/5. The probability of A is 1/3. The probability of B is 2/5. And we're looking for the probability of A and B. So if we do some rearranging of our equation, we can bring over the probability of A and B, making it positive. And that leaves us with 1/3 plus 2/5, and we're going to bring over the 3/5, so subtract 3/5. And so the probability of A and B is 2/15. Now we have to then check to see if that fits our criteria for independent events. So we're going to make our table, our left side, right side table. We're going to look at the probability of A and B. And we're going to look at the probability of A times the probability of B. Well, the probability of A and B is 2/15. The probability of A is 1/3. The probability of B is 2/5. And if we multiply that out, that gives me 2/15. So this is independent. So it's independent, but not mutually exclusive. That means that when we're looking at our experiment, one outcome does not affect the other, but there is an overlap in the outcomes that we're going to get. All right, let's continue on to some more examples here. So example number 5 says to let event A and event B be events with the probability of A being 1/2, the probability of B being 1/3, and the probability of A and B equaling 1/4. And we're being asked to determine the probability of B given A, the probability of A given B, and the probability of A or B. All right, so let's take a look at the probability of B given A first of all. Now, because it's B given A, that means we're looking at the probability of A and B. equaling the probability of A times the probability of B given A. Had it said A given B, then I would have written the probability of B and A. All right, the probability of A and B is 1/4. The probability of A is 1/2. And we're looking for the probability of B given A. So in order to solve this problem, I'm going to have to take 1/4, divide by 1/2. And so the probability of B given A is 1/2. Again, because I took the 1/4 and I divided by 1/2. All right, so the probability of A given B, well, now I have the conditional probability being A given B, so this is going to be the probability of B and A, which is just the same as that one there, equals the probability of B times the probability of A given B. So while we're going to be using some of the same numbers, the notation is slightly different. So the probability of B and A is 1/4. The probability of B is 1/3, and we're looking for the probability of A given B. So 1/4 divided by 1/3 will give me 3/4. Now the last question here is the probability of A or B. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So the probability of A or B is what we're looking for, and that's going to equal 1/2 plus 1/3 minus 1/4. And the probability of A or B will be 7/12. So this is one where we can just take those numbers and plug them directly into the formula. All right, 2 more examples today. Example number 6, it says the probability that Taven will pass math this semester is 0.7, and the probability that he will pass English is 0.9. We're told right off the bat that these events are independent. So if these events are independent, we're going to determine the probability of each of the following situations. So the first one, we want to figure out the probability that Taven passes both math and English. So we want to check out the probability that he will pass both math and English. So the probability of math and English. Well, that's going to be the probability of math times the probability of English, because we're told these are independent events. So the probability of passing math is 0.7. The probability of passing English is 0.9, and we have 0.63. So again, and in math means multiply, and there's no conditional probability to worry about, so we're just multiplying our numbers. Or, what's the probability of passing math or English? Or means add. So the probability of passing math or English is going to be the probability of passing math plus the probability of passing English minus the probability of passing both. Now, if the probability of passing both was 0, then we would just subtract 0. But these are not mutually exclusive events. It is possible for Taven to pass both courses. So the probability of math is 0.7 plus the probability of passing English is 0.9 minus the probability of passing both, which we just did in the last question, is 0.63. So there is a 0.97 chance that Taven will pass both courses. So a 97% chance of passing both. All right, what about the probability of passing math but not English? So that's the probability of passing math and not passing English or failing English. So that's going to be the probability of passing math times the probability of failing English. So probability of passing math is 0.7. If the probability of passing English is 0.9, then the probability of failing English is 0.1. So that gives us 0.07. And neither nor. So neither math nor English. So that's the probability of failing math and failing English. So that means they're going to fail both. So the probability of failing math times the probability of failing English. So the probability of failing math is 0.7 because the probability of 0.3 because the probability of passing was 0.7. And the probability of failing English is 0.1. So when we multiply those out, we get 0.03. So a 3% chance of failing, which makes sense because if you look up here, we have a 97% chance of passing. We have a 97% chance of passing, then we should have a 3% chance of failing. So 0.97 plus 0.03 equals 100. All right, let's take a look at our last example here. So a number is selected from the first 10 natural numbers, and we want to consider event M, a prime number is chosen, and event N, an odd number is chosen. And so anytime we're doing these questions, it's really helpful to start off by listing all of your information. So starting off with your sample space. So we're choosing a number from the first 10 natural numbers. So we go back to our set notation, start off by writing out our sets. So our sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there's our sample space. Again, you can do this with a Venn diagram. We have event M being that a prime number is chosen. Remember that 1 is not a prime number. So 2, 3, 5, and 7. 9 is also not prime. That's a common mistake some people will make. 9 is odd, but it's not prime. Event N is an odd number is chosen. So this is going to be 1, 3, 5, 7, and 9. And then the M and N, so the event M and N is going to just be 3 and 5. Oh, 3, 5, and 7. So the overlap between the two is 3, 5, and 7. And then M or N, this is listing all the outcomes that are in both. So we have 1, 2, 3, 5, 7, and 9. So whenever you're giving these questions, it's really helpful to list your sample space. Essentially, you're listing your sets and your subsets, and then from there, it's easier to determine your probabilities. So we're going to consider the probabilities for each of these. So the probability of M occurring is 4 out of 10, which reduces to 2/5. The probability of N occurring is 5 out of 10, which is 1/2. The probability of M and N occurring is 3 out of 10. And the probability of M or N occurring is 6 out of 10, which is 3/5. Again, this is just practice in setting up your probabilities and determining them. But now we're going to look at the conditional probabilities. So part C says to determine the probability that a prime number is chosen given that an odd number is chosen. So using our formulas, we're going to have the probability of N and M equaling the probability of N times the probability of M given N. And we have all of the numbers that we need up top, so we're just going to solve here. So we have the probability of N and M is 3 over 10, and that equals the probability of N, which is 1/2, times the probability of M given N. So to solve, we're going to take the 3/10 and divide by the 1/2, and we're going to have the probability of M given N being equal to 3/5. Now, Bennett looks at this question and says, well, wait a minute, there's got to be an easier method to using a formula. And he says that if we just take a look at the answers above, we could look at the number of odd numbers in the sample space and count how many of these were prime and then set that up. So he's going to say, well, let's just look up there. We have 1, 2, 3, 4, 5 odd numbers. And of those 5 odd numbers, we have 3 of them that are prime. And so that's 3/5. That's the probability. So the probability of m given n is 3/5. Essentially, take that n value, make it our denominator, and then figure out the probability out of there. So the answer is it correct? And the answer would be yes. Or the question is it correct? And the answer is yes. So when we're looking at this probability of m given n, we're basically saying that the set n has 5 elements, of which 3 are prime. So let's take a look at this here. So if we want to determine the probability of an odd number being chosen, given that a prime number is being chosen. So the probability of odd given that they're prime. Well, if we use Bennett's method, we look at m, there are 4 prime numbers, and of those prime numbers, 1, 2, 3, 4, 3 of them are odd. So 3/4. So this would be Bennett's method. And then we can also take a look at the formula method. So the probability of n given m is going to be the probability of m and n equals the probability of m times the probability of n given m. Well, the probability of m and n is 3/10. The probability of m is 2/5. And we're looking for the probability of n given m. And so to solve this question, we're going to take the 3/10 and we're going to divide by 2/5. So the probability of n given m is also 3/4. So with that conditional probability, you can essentially treat this almost like your fraction right there. So the m is the 4, and of those 4, 3 of them are odd. All right, so this is the end of the lesson. Hopefully I've given you enough examples. In the next lesson, we're going to be looking at all of our probabilities again, but we're going to look at some other strategies to solve, such as using tree diagrams and tables and so on. All right, that's all for today. Have a great day, and we will see you soon.